So yeah, my name is Atanas Kiryakov. I'm founder and CEO of Ontotext. We are the developers of GraphDB, and Ontotext was also one of the founding partners of the Linked Data Benchmarking Council some 10 years ago, together with Neo4j, OpenLink, CVI, and a few other organizations. So where it all started was with these two benchmarks, the social network benchmark that Gabor presented before, and the semantic publishing benchmark. That was actually our contribution and development. Next slide, please. So now, almost 10 years later, what's going on is that we did a round of benchmarking with the with the semantic publishing benchmark when it was first developed, 2015, and published it. And then for a period of time, we've been quiet. And also historically, it was always RDF engines never went for the social network benchmark because the design is to a good extent influenced by more like Neo4j and LPG engines, and it was considered a different ball game. Now more and more we see these different technology stacks in graph databases converging, and the team of Tomas actually did all the effort to first implement the relevant traversal mechanisms and optimizations in GraphDB, and also to make the necessary implementation for this RDF/Sparkle version of social network benchmark so that we can run it. And we are very happy that we get the support of Gabor and other people who also got on board with benchmarking and auditing these results, which was an organizational challenge. So today we will present our first results for the social network benchmark, and this is the first result from an RDF engine for it, as well as updated results on the semantic publishing benchmark. With this, I'm handing over to Tomas, who is the lead engineer of GraphDB.
Okay, so everyone again. Before we delve into the basically our extension of SNB and how we made it compatible with RDF and namely GraphDB, I want to mention that graph algorithms and basically the use case of social networks involves a lot of graph traversal, which in the case for Sparkle 1.1 is not very efficient. That is why we need, as Naso mentioned, we needed to introduce our own path search extension that is actually Sparkle 1.1 syntax compliant, and it allows us to do a sort of short path traversal or path traversal and finding the distance between two given nodes or starting a single node to multiple nodes. That was part of the steps that we needed before we actually started implementing the benchmark itself. The next part was actually researching and reviewing all the different queries from the short load and from the short query load and from the interactive query load, which we implemented using Sparkle. So we are proud to say that we didn't use any sort of imperative language or stored procedures. And as for the data loading, we actually use the standard SNB Hadoop data generator in order to pass the benchmark itself. So what were the challenges that we faced while passing the benchmark? Well, one of the main things was the complex query plans. So you had multiple hop queries where you actually matched the friends and friends of a friend, for example, of a given person with joins of related metadata such as posts and tags relating to those posts. So you had some different possible how can I say it, bottleneck indicators such as data access locality and so forth. And based on those ones, we actually introduced our Ontotext approach, where we improved the path traversal algorithms and used inference in order to materialize shortcuts in the graph. In terms of the path traversal algorithms, we optimized the path search traversal algorithm to basically leverage our global entity pool, meaning that we did not use any literals or resources or any sort of large string or any object inside the database, but we used IDs. So based on those primitive IDs, we actually managed to save a lot of memory since the path search extension is in-memory based. And also for the shortest path traversal algorithm, we implemented a greedy approach where, given a start and end node, we actually managed to cut significantly the processing time when we started using this greedy approach, where we iterate the adjacency list on which side is smaller. And basically, we wanted to challenge our implementation of path traversal, and for that, we did a small test against the standard LPG engine. And these are the results in the table below, which you can see for the OPAF search, where a standard LPG engine would have a performance of roughly 4 seconds, compared to GraphDB, whose performance is roughly 1.6 seconds for the scale factor 10. And again, for the shortest path algorithm, a standard LPG engine would perform for roughly 2 seconds, whereas our performance was for 800 milliseconds. And in both cases, our performance was roughly 60% better. And as for the inference shortcuts that we used, basically RDF engines are good for reasoning, which is all about creating shortcuts in the graph. And this actually helps shorten the path between nodes. And that actually allows us to scale better with larger data sets, especially where we need to traverse more dense graphs where the adjacency lists are larger. So here we have a small example of query 11 from the interactive query load, where usually you would implement it in the RDF data model with a blank node that has a relationship which stores basically the relationship metadata between a friend and friend of a friend. And well, in that case, the query would have 4 hops before it reaches that friend of a friend, whereas with the shortcuts implemented through our inference engine, that query took only 2 hops. So that resulted in a 25 times faster performance for some of those queries that involved short path traversals. And basically, it allowed us to scale much better with the scale factor 30 dataset. So now I hand over to Naso, who summarize our experience.
Yeah, to wrap up our experience with the social network benchmark, we prove it's a doable thing for an RDF engine with its scale factor 30, which is 1.55 billion edges. We intentionally run all these benchmarks and got them audited on standard Amazon AWS instances. In this case, R6ID 8X Warch, which is a relatively big machine, but nothing stunning. We were able to get, it's not a big figure in terms of operations per second, like 12 operations per second. But we had all the nice features, like it scales when you get more agents running queries in parallel, simultaneous agents. It works well with updates and everything that you expect there. What is actually very, very important for this result is that this is the first published result and audited result from a system that is running it as a database should run it with a declarative query language. In our case, it's Sparkle. If you go to the social network benchmark page, you'd see that all the other results involve some C++ coding or stock procedures or something like that, which is probably not the main purpose of most of the benchmarks, where you mean I have a database and it has a query language and let's see how good it is. So that's the first result of this type. It doesn't look as impressive as what Gabor showed in the previous time slot, but it's also a completely a different discipline of doing proper queries and optimization and stuff, or implementing something in C++. So that's the wrap up here. We're very happy that we passed it. We'll keep working to optimize. Now, going to the semantic publishing benchmark, we developed this one based on a use case by BBC. They were actually the first adopters of in like mission critical scenario of an RDF graph database. So they made a website for the FIFA World Cup into 2010, where essentially they used had a lot of metadata about all the content related to this big sport event. All the content was properly enriched with a lot of metadata, like who players is this article about, or this video and stuff like this, and all the relationships between the players, the teams, the coaches, and so on and so forth. So in the middle of these, there is a reference dataset, reference graph with all the important entities about the event and all the relationships between them and the important information about them. And then you have a big mass of creative works, which are described by references to this reference knowledge in the middle. So that's the essence of it. And what they were using it for is essentially they had topical web pages, thematic web pages on the website of BBC for this event, for each player, each team, each stadium, if you want, each group in the play. And these pages were automatically generated by Sparkle queries, like 5 Sparkle queries per page. So you can imagine that at the top of the event, it was very, very, very heavily loaded, and they keep using this technology in this pattern for their sports website and for other parts of it. And there also is a fair amount of updates, because as the time goes, there are new scores and new information and new creative works, and once in a while there is something to be changed in the reference knowledge also. So what makes this benchmark interesting is that it is a heavy load with queries. They call it aggregation agents, which pull data out, and there are a lot of updates that should be processed instantly. And on the technical side, it involves inference, geospatial constraints, full text search, and few other checkpoints. So it's really a very complex benchmark. Next slide. Next slide, please. Yep, thank you. Okay, so we did it in 2 scale factors. We'll speak more about the bigger one, which is 1 billion statements, more or less the same size like what we've seen with SNB scale factor 30. And there is a single workload with 12 aggregation agents and 2 update queries. One is cert, one update. We run it on the same machine, and we experimented with 2 configurations: a single server and also a high availability with 3 nodes. Thomas, over to you.
Okay, so with this benchmark, as Nasu mentioned, basically the point is to be able to validate a number of choke points for a database engine, and to mimic a real-life use case scenario as close as possible. That is why we decided to sort of showcase our the database engine in terms of how cloud ready it is, and as well as how enterprise ready it is. So in terms of having a cloud ready graph database, basically we're happy to say that all of these results that we've basically audited are easy to replicate, and it could be done with our Helm chart or with our Docker images for both a single instance or a clustered setup. And no parameter tuning is required to match the performance from the audited results. So in terms of the actual benchmark results, you can see here we have 2 extracts. So the first one is based on 3 various AWS machines. So first one, the I4I, is the smallest machine, M6ID is larger, and R6 ID 8X large is the largest of the three machines, and it is the one on which we actually audited all of our results. So you can see that as a cloud-ready database, we try to scale as much as possible with the available hardware. So you can see with the smallest machine possible on the 1 billion benchmark of SPB and with 16 concurrent read agents running, we actually managed to achieve roughly 70 queries per second. Whereas with the better M6 ID or larger machine, we actually managed to achieve 100 queries per second, whereas the cost for those machines actually increases in this similar, roughly linear pattern. And also for the R6 ID, which is the largest of the three machines, we actually managed to achieve 130 queries per second based on 16 concurrent readers. And that performance is almost twice as good as that of the smaller machine. And the cost of that is based on the reserved machine for 1 year, so as of 2023. And basically, we wanted to showcase how that kind of performance can be achieved with various types of instances and how larger hardware basically allows GraphDB to scale even better. So in terms of having an enterprise-ready graph database, we decided to use our high availability cluster, which is based on replication of data between nodes. So it's not a sharding cluster. And basically, we wanted to showcase that we can provide high availability and fault tolerance at the same time where you have scalability in terms of read queries and where you could actually load balance those queries to all of the instances in the available resources. So here we have an extract from the audited results with a GraphDB cluster setup of 3 nodes using the same machines that we showcased in the previous page of R6 ID 8X large. And here we can see how, for example, for 16 read agents on the 1 billion dataset, we have roughly 180 queries per second, whereas with 64 concurrent reading agents, we have roughly 410 queries per second. And that kind of performance is almost 2.5 times better than for the 16 read agents, meaning that our load balancing component of the cluster is able to basically effectively distribute those queries to all the available nodes. And for the smaller data set of 256 million statements, we actually managed to achieve 1,000 queries per second for 64 read agents. And that kind of performance is basically available to be tested out using all of the available AWS instances with the standard GraphDB cluster. So no need for extra setups. And on top of that, basically, we managed to achieve high availability and fault tolerance at the same time while we are serving 1,000 queries per second. And that is taken into account the fact that the SPB benchmark in itself compares various bottlenecks, including full text search, full scan queries, and so forth. So, Naso, I pass over to you.
Yeah, let's wrap up because we're a bit ahead of time. Okay, what we are very, very proud with is that we GraphDB is the first engine that can pass both SPB and SNB, which was a good thing to have with all the different complexities and a lot of graph analytics on the one end and everything else like geospatial and inference and full text search on the other. Again, I hope that in the future we'll see more results for the social network benchmark that come from proper declarative query language implementations rather than C++. And yeah, I do believe, and that's one example how all these benchmarks and LDBC all together is helping competition and development of the engines. It took Tomas' team about 2 years to get to these results on SNB that you see now. Thank you.
Thank you.